All right, so the recording has started. So this will be the last part, right? Uh, Last part of diffusion models. Let me share my screen again. Right. So this will be diffusion model 4. Okay. All right. Let's see the last part of the diffusion model. This is number 12 in diffusion models. This is the fourth part. Uh, okay. So till now, what have we seen? So till now, I mean, the things are quite simple. I mean, we haven't actually complicated things. I mean, the underlying thing at least is the same, right? So you have x naught, x1, so on till x capital T. There is a transition kernel q of x1 given x naught, and in general, there is q of xt given x t minus 1. Right? And then there is a reverse process that is modeled using a neural network. This thing in general models p theta xt given xt plus 1, something like this, right? Uh, the forward process is quite easy because you actually using all of this, you can also can directly get what is q of xt given x naught. So forward process is quite simple. However, we saw how we can learn the parameter theta of the reverse process, particularly by uh, uh, assuming that p theta is a Gaussian distribution and modeling its mean using a neural network, and we saw the form of the mean that it can take, and so on and so forth. Right. So let's take a step back. Okay. Let's take a step back. We saw in the last lecture that how you can learn the uh, uh, learn the parameters if you want to. But where I want to go back to is this part. The Without assuming what is the form of mu theta, what was the objective? The objective was it looked something like arg min over theta 1 by 2 sigma q square mod of norm of mu theta minus mu q norm square. So what are we going to see in this last part is that there are three equivalent interpretations of diffusion models. Okay, one of them we have already seen. Okay, so there are three equivalent interpretations. So first one is the X naught prediction interpret interpretation that we have already seen, right? Particularly here itself, we saw that I mean, your x theta hat can be used to predict the x naught directly, right? That is what the loss function was. There is another interpretation here, which is epsilon prediction, which we will see. Epsilon prediction interpretation. And there is another one, which is what will lead us to the next module of our course, which is score prediction. Score prediction. Score prediction. Right. So this part we have already seen. This thing we have already seen. This part we have already seen. Right? I mean, till now we have been working with that itself, right? Let us look at the second and third one. Okay. So let us look at the second one, epsilon prediction. Let us see what this is. Okay. So what is this epsilon prediction thing? Uh, well, it's quite simple. So we know what q of xt given x naught is, right? So we will again come back to this equation itself, okay? This equation itself directly. Let us see what that is so that we can let's look at it. So okay, q of xt given x naught was something which is a Gaussian. Because xt was centered around root of alpha t bar x naught, comma 1 minus alpha t bar epsilon. Let's call it epsilon naught. Okay, right? So epsilon naught is, I mean, okay, sorry. Well, this was I. Okay. Anyway, I mean, this is what the transition kernel from x naught to xt was. So using this thing, you can directly write xt as root of alpha t bar x naught plus square root of 1 minus alpha t bar epsilon naught, where epsilon naught is coming from Gaussian 0 I. Okay, this is fine. Okay, from here, what you can do is you can directly write what is x naught, right? I mean, you can directly write what is x naught. So what is x naught? X naught here is xt minus square root of 1 minus alpha t bar epsilon naught divided by square root of alpha t bar. This is what x naught is. Cool. Okay. Let's keep this in mind. Now let's go back to our this equation. Here, what is the value of mu q? If you remember, when we derived this x naught prediction interpretation, what we did was we wrote down what was mu q here, right? And we saw that, okay, what are the things that we know in mu q? We knew this term, but we didn't know this term. So we parameterized it using a neural net. What we will do is we will again write down this same thing, but instead of x naught, we will write it in a different way so that we'll, we will write x naught in a different way. And then we will see what are the terms we know. And we will again choose our mu theta such that, uh, I mean, similar to what we did here, that we know this term, we know this term, we'll write it, and whatever is unknown, we will parameterize it. We'll do that thing. Okay. So let's do that. So mu q of xt comma x naught, what was this thing? So this was actually root of alpha t, 1 minus alpha t minus 1 bar xt plus square root of alpha t minus 1 bar 1 minus alpha t x naught, right? Divided by 1 minus alpha t bar. This is what it was, right? Now from this equation, from this is, maybe let's call it just 1. We can substitute 1 in this equation, right? What will that lead to? This will become root of alpha t 1 minus alpha t minus 1 bar xt plus square root of alpha t minus 1 bar 1 minus alpha t. What will be x naught? So now let us substitute this thing, right? So x naught is what? X naught is xt minus square root of 1 minus alpha t bar epsilon naught divided by square root of alpha t bar. This is what it is. This whole thing divided by 1 minus alpha t bar. Right? I have just substituted x naught here from this equation. That's all. Is this fine? Like nothing fancy, just substituted x naught directly here.
Yes, yes.
Okay. So from here now, let's simplify this. What can be simplified? Okay, first of all, let's note that this thing will get cancelled straight away, right? Is there any other thing that can get cancelled? No. So this thing will be just as it is. Oh wait, alpha t. Oh wait, sorry. So this is alpha t and this is alpha t minus 1 bar. So we cannot directly cancel it. So this thing is alpha t bar, right? Alpha t bar can be written as alpha t into alpha t minus 1 bar, right? So now we can
Yes.
cancel this thing and this thing. Yeah. This thing can be cancelled. This thing will become alpha t 1 minus alpha t minus 1 bar xt plus uh, become 1 minus alpha t into xt minus square root of 1 minus alpha t bar epsilon naught divided by square root of alpha t. Okay, whole thing divided by 1 minus alpha t bar. This is what it has become. Now let us like just write things in simpler way, right? Let us write it down. So what I will do is I will just break down the terms. 1 minus alpha t minus 1 bar xt thing divided by 1 minus alpha t bar, right? This is the first term plus uh, 1 minus alpha t xt divided by 1 minus alpha t bar square root of alpha t, right? That's the second term here. And minus the third term, which is what? 1 minus alpha t square root of 1 minus alpha t bar epsilon naught divided by 1 minus alpha t bar square root of alpha t. This is what it is, right? I have just simplified, I mean, just broke down the terms and I have written them as separate things. That's all. Okay, now let's club these xt and xt terms, right? So this will become, yeah, sorry, this will become square root of alpha t 1 minus alpha t minus 1 bar divided by 1 minus alpha t bar plus 1 minus alpha t divided by 1 minus alpha t bar square root of alpha t whole thing xt, right? Minus 1 minus alpha t square root of 1 minus alpha t bar divided by 1 minus alpha t bar square root of alpha t epsilon naught. This is what it is. Cool. Uh, Now what we will do is simplify the thing that is inside the associated with the xt, right? This thing. So let's do that. So what do we need? So 1 minus alpha t bar is common here. We need to multiply by root of alpha t in the numerator. So that will make it alpha t, root of alpha t into root of alpha t will become just alpha t. So 1 minus alpha t minus 1 bar, right? Plus 1 minus alpha t, which is already there, whole thing divided by square root of alpha t xt minus 1 minus alpha t square root of 1 minus alpha t bar 1 minus alpha t bar square root of alpha t epsilon naught. Okay. Now, is anything getting cancelled? So you have, so this thing, I mean, again, our old trick, this thing is equal to alpha t minus alpha t into alpha t minus 1 bar. This thing is nothing but alpha t minus alpha t bar, right? This is what this thing is, this thing. So alpha t minus alpha t bar plus 1 minus alpha t. So this alpha t and this thing will get cancelled, right? So this leaves us with what? this will become uh, 1 minus alpha t bar, that's all. So, so this will become 1 minus alpha t bar divided by square root of alpha t into 1 minus alpha t bar, right? Minus 1 minus alpha t. There is a square root of 1 minus alpha t bar here and 1 minus alpha t bar in the denominator. That will make it square root of 1 minus alpha t bar square root of alpha t epsilon naught. And this is xt here. This thing again will get cancelled out. This thing will become simply 1 by square root of alpha t xt minus 1 minus alpha t divided by uh, square root of 1 minus alpha t bar square root of alpha t, no, just alpha t epsilon. Okay, so this is what your mu q of xt comma epsilon naught is. So basically I did that substitution here where I wrote x naught in terms of epsilon naught, xt and epsilon naught, right? And then we did a lot of simplification. You can ignore all those simplifications if you want. But end of the day, x naught got omitted. Instead, we were able to write mu q in terms of xt and epsilon naught. Remember, remember what was epsilon naught, right? Epsilon naught was this noise that we added to x naught in order to get xt, isn't it? So epsilon naught is the noise that we added in order to obtain xt. Just remember that. So now this is our mu q. So remember here, right? Back when we did this derivation, we substituted mu theta to have like we put mu theta to have a form which, so again recall what we did there, that mu q had a certain form. We said that we can make mu theta as close to mu q by setting things that we know. I mean, so like by setting things that we already know. So for example, this term is something that we already know, so we can just keep it as it is. The denominator is already known, the scalars are already known. What was unknown was x naught. So for x naught, we used a neural network, right? Similarly, using same argument, this is mu theta of xt. What we can do is, we know xt, right? So the first term, we can write it as it is. So this will become 1 by root alpha t xt minus, these scalars are predefined, so we already know them. So this is 1 minus alpha t divided by square root of 1 minus alpha t per square root of alpha t. However, here is the catch. We don't know what is epsilon naught, right? We don't know what was the noise that was added to x naught in order to obtain xt. So this is the unknown. So what we can do is, instead of having using epsilon naught, we can use a neural network here, epsilon theta hat of xt comma t. So this argument is very similar to what we did here, but instead of x naught, we are using epsilon theta,
Yes, yes.
right? So if that is the case, then what will be our loss function finally? What will this loss function become finally? So this is so what is this side? Okay, so remember what was this loss function? This is the loss function, right? So this is arg min over theta, right? This is arg min, that implies arg min over theta over 1 by 2 sigma q of t square norm of mu theta minus mu q whole square. This was our loss function, right? Now let's substitute mu theta and mu q and see what happens, right? This is equal to arg min over theta over of 1 by 2 sigma q square. What is mu theta? Mu theta is 1 by root alpha t x t. Okay, of course there is a norm outside xt. Okay, minus 1 minus alpha t divided by square root of 1 minus alpha t bar square root of alpha t epsilon theta hat of xt comma t. Okay, this is your mu theta minus mu q. What is mu q? It is the same thing except we have epsilon naught here, right? So I'll just write it down. 1 by square root of alpha t xt plus 1 minus alpha t square root of 1 minus alpha t power square root of alpha t epsilon naught, right? This thing whole square, this is what it is. So now what will happen? Again, the benefit of doing such parameterization is that things get cancelled out. This thing gets cancelled out simply, right? And this thing will become argmin over theta of 1 by 2 sigma q square. What will come outside is these constants are like will come out of the norm, so that will become 1 minus alpha t square divided by alpha t into 1 minus alpha t bar, right? And the norm will be just epsilon theta, uh, sorry, epsilon naught minus epsilon theta of xt comma t at this thing whole square. So this is what, so this is another version of the same loss function, right? Uh, here epsilon theta is your neural network that learns to predict the noise epsilon naught that was used to determine xt using x naught. So we have shown that the diffusion model, you can learn the diffusion model by predicting the original image x naught, right? That was our original formulation. But that prediction, you can also learn it. This is equivalent to learning to predict the noise, right? Uh, so both of these things are similar. That is the point. Like if you predict x naught or you predict epsilon naught, both of these things are equivalent. There is one note here that empirically, empirically, epsilon naught prediction works better. Prediction works better. This is a empirical observation. Usually, you will see that in most of the implementations, uh, this is what is done. So you predict epsilon instead of x naught.
Yes, can we further simplify this expression because we know the value of sigma q square in terms of the alphas, I mean, in the previous slide.
Sorry, what?
Can we further simplify this loss function by putting the value of the sigma q square because we know its value, I mean, in terms of the alphas in the
Yeah,
previous
I
slide.
think you can. So maybe you can. So yeah, you can perhaps maybe I haven't tried it, so maybe it will become something like argmin. But I don't know if it will come out in terms of SNR. Okay, so should we do it? Do you want me to do it right now?
No, I will try on my own. I mean, whether this, I mean,
Yeah,
will this result into
I think
something
that's
fruitful?
yeah, could be something, yes. So this is the second version or second interpretation of your diffusion model. Okay. There is this last interpretation, which will basically be the end of diffusion models for us, okay, which is score prediction, okay. So this was, remember that this was epsilon naught prediction. This is the noise prediction version. So we have completed this thing. This thing is completed, okay. Let's look at the last one, the third one, which is the sort of the interesting thing, which is the score prediction interpretation. What is it? Okay, so the third one, this is the score prediction interpretation. Okay, so what is this thing? Uh, so we are going to need one thing, which is something called Tweedy's formula. 3D's formula. What is the studio? So this is actually something which is very useful in research, actually. Even my work revolves around this formula. But it's quite interesting. I'll just tell you how. Okay. What is it telling you? What is so I'm giving you a very and so it's a very informal way to state the 2D's formula. So let's say that you have a Gaussian random variable z coming from a Gaussian distribution, right, with some parameter, some mean mu and some variance sigma z, okay, something like this. Then 2D's formula states that expected value of mu z given z. So, for example, so let's say that you have one observation from this distribution. So you sampled something from this distribution z. Okay. Having seen this distribution z, what is the expected value of your mean? Like, I mean, you want to estimate your mean, right? I mean, like you want to know what is the mean of my distribution from which I have sampled this sample. Today's formula tells you that expected value of mu z given z is nothing but z plus sigma z gradient z log e of z. So this might look very weird at first, but uh, uh, like I will tell you the what is the interpretation. So the idea is you want to know what is the expected value, what is the mean of the distribution, okay? But you only have one sample to make that make that you have only one observation to make that estimation. So just by seeing Z, can you tell me what is the mu Z? That's the question. And 2D's formula gives you a for like gives you an expression for that. It tells you, okay, the expected value of mu Z given Z is Z plus your variance or covariance times this thing. Okay. This thing, this thing is this thing is some is also called score function. This
So
grad
is it,
log PZ is also called score of a distribution. Yeah, sorry.
yeah, so is this formula valid for the continuous distribution or for the discrete
Yeah,
one also?
see, for discrete, there is no gradient defined. I mean, the gradient should be defined, right? For discrete, you don't have differentiability, so you cannot define this thing.
Okay,
You need to have a like differentiable support in order to uh, talk about the score function.
okay.
Yes. So in this case, so we will just take this formula on the face of it, okay? But this is a very important formula. I mean, a lot of the current research is driven by this formula actually. So I will tell you why. I will give you a like a sneak peek into why. So let's think about it. So you have q of xt given x naught. This is again a Gaussian distribution, right? This is a Gaussian distribution. This is Gaussian of xt centered around root of alpha t bar x naught, comma 1 minus alpha t bar I. This is what it is, right? We know this. So then by 2Ds, we can use the 2Ds formula, right? What will that tell us? It will tell us that expected value of mu xt given x naught. So remember that, sorry, given xt. It so today's formula tells you the expected value of the mean given a sample from the distribution. So given xt, what is the mean of the distribution? This thing is equal to xt. I'm just writing this thing down, xt plus what is the covariance? Covariance is just 1 minus alpha t bar I. So I we can just ignore that. 1 minus alpha t bar grad of xt log p of xt, right? This is what it is. This is applying 2D's formula on top of our forward process. That's all, right? So
Yes.
what we can do here is we can do something interesting here actually. So, but actually we know what is So think about it. We already know what this thing is, right? What is this thing? This thing is root of alpha t bar x naught, isn't it? So your mean, like, uh, I mean, the best mean. So this is like, so according to TD's formula, the best estimate for the true mean that xt is generated from is this thing itself, right? We know what is the true mean of the distribution, which is square root of alpha t bar x naught. So this thing is actually equal to square root of alpha t bar x naught, isn't it? Because we know what is the distribution, but by TD's formula, we know another way to write the mean. So we can just compare these two things directly, right? In
Yes.
that case, in that case, what will be x naught? We can write what is x naught here again. X, so this is the numerator xt plus 1 minus alpha t bar. So I will just write grad. I will omit this with respect to xt, but we can always know that whenever we are talking about the score, it's the gradient is with respect to the argument here, which is xt log p of xt divided by square root of alpha t bar, right? This is what it is. Now, similar to what we did again, like again, the process is always the same. So again, let us write down what is mu q of xt comma x naught. What was it? So this is square root of alpha t. I mean, we have written this multiple times now. Xt plus square root of alpha t minus 1 bar, 1 minus alpha t x naught divided by 1 minus alpha t bar. Okay. Uh, if this is the distribution, what we will do is again the idea is quite simple. This is the x naught value. We'll substitute it here. That's all. So let's do that. So it will become square root of alpha t 1 minus alpha t minus 1 bar xt plus square root of alpha t minus 1 bar 1 minus alpha t. What is the value of x naught? Value of x naught is xt plus 1 minus alpha t bar grad log t of xt whole thing divided by square root of alpha t bar, which is alpha t into alpha t minus 1 bar. Okay, this whole thing divided by 1 minus alpha t bar, right? Again, this thing and this thing gets cancelled out. Let's write it down. So this will become square root of alpha t 1 minus alpha t minus 1 bar xt plus this is 1 minus alpha t x t divided by square root of alpha t plus 1 minus alpha t 1 minus alpha t bar grad log p of xt whole thing divided by square root of alpha t, right? Um, is it correct? Yes. The whole thing divided by 1 minus alpha t bar. Okay. Nothing. This I'm just simplifying things. Now again, club the terms that have xt in it. Same old thing, right? Nothing fancy. So I'm just like fast forwarding something. So this will become alpha t into 1 minus alpha t minus 1 bar plus 1 minus alpha t whole thing divided by square root of alpha t 1 minus alpha t bar xt, right? Plus this is okay, so things might cancel out here. 1 minus alpha t 1 minus alpha t bar grad log p of xt, okay, whole thing divided by 1 minus alpha t bar into square root of alpha t, right? This thing gets cancelled out, right? Again, our old trick, this thing is equal to alpha t minus alpha t into alpha t minus 1 bar. So this is alpha t minus alpha t bar. So in that case, this alpha t, right, sorry, that case, this alpha t and this alpha t gets cancelled out. So this thing becomes 1 minus alpha t bar divided by square root of alpha t into 1 minus alpha t bar xt. This thing will again get cancelled out, plus 1 minus alpha t whole thing divided by square root of alpha t grad log p of xt, right? This thing becomes what? This thing becomes 1 by square root of alpha t xt plus 1 minus alpha t over square root of alpha t grad log p of xt. Now this is your, which is equal to your mu q of xt comma grad log p of xt. This is what your new mu q is. Okay. So now this time your mu q is function of xt and this core function itself. Now what you can do is you can write your mu theta as function of xt comma t to be equal to, you take the same form, right? 1 by square root of alpha t xt, because you know what is xt, you know what are alpha, so you write this thing as it is. So square root of alpha t. You don't know what this thing is, right? You don't know what is the score function because you don't know what is this p of xt. You know, so that's the problem. So again, what we don't know, we will parameterize it using a neural network and we will learn it as theta of xt comma t. Okay. Now, again, like similar to what we did earlier, that you want to minimize this thing, right? You want to minimize your, this is your original objective, right? So this is argmin, this is argmin over theta 1 by 2 sigma q of t whole square norm of mu theta minus mu q norm whole square. This is what it is. So let's write this thing down. This is equal to argmin over theta 1 by 2 sigma q of t whole square. What will be your, what is your mu theta? Now mu theta is something that is known. What is root alpha t xt? And just repeating whatever we have done till now. Square root of alpha t as theta of xt comma t. Okay, this is mu theta. What is mu q? Mu q is just the same thing, uh, but with the original score function. So this is 1 minus alpha t square root of alpha t grad log p of xt. This thing norm whole square, this is what it is. Now again, things will get cancelled out. That is the beauty of such parameterizations, right? And what will be your final loss function? This will become arg min over theta 1 by 2 sigma q whole square into this constants will come out, right? So the constants will come out that will make it okay. So first thing is that this thing will become minus. So what is the constant? The constants are 1 minus alpha t whole square by alpha t norm of s theta of xt comma t minus grad log p of xt whole square. Right. So this is another version of your uh, diffusion mode, another interpretation of your neural network. So here, S theta is the neural network that learns to predict the score function, that is grad log p of xt, which is the gradient of xt in data space for arbitrary noise level t. Okay.
And how
Now,
difficult it is to compute the gradient?
so yes. So, okay. Now, actually, so this is what we will discuss in the next model, which is score-based model. We will talk about the difficulty that is involved in calculating grad, this gradient of log p of xt, and so on and so forth. We will see that,
Okay, okay.
but we will discuss those things very in great detail. But another thing to note here is, which is sort of interesting, is in the epsilon prediction framework and in the score prediction framework, there are quite some similarities, right? What is the similarity? So in both the things, what we did was we tried to write x naught in terms of epsilon or the score function, right? For example, we wrote for epsilon prediction, we wrote x naught as xt minus 1 minus alpha t bar epsilon naught divided by square root of alpha t bar. We wrote this thing, didn't we? This is where this is how we substituted, right? This thing, right? This thing. We wrote x naught in terms of epsilon naught first. Then similarly, using Tweedy's formula, we wrote x naught in terms of this gradient as well, right? In terms of this score function as well. So this thing, so we can actually write both of these things. So this thing is also equal to what we wrote in terms of the score function, which is 1 minus alpha t bar grad log p of xt whole thing divided by square root of alpha t bar. Now, a natural question to ask is, we know what is the relation between x naught and epsilon naught. We know what is the relation between x naught and the score function. What is another, like a logical question to ask is, what is the relation between epsilon naught and the score function? So, uh, if we compare the second and third term here, right? You can clearly see that, well, xt will get cancelled out, this thing will get cancelled out, and what will be left with? So we can see that 1 minus alpha t bar grad log p of xt, this is equal to uh, minus square root of 1 minus alpha t bar epsilon naught, right? And this implies that the score function here, grad log p of xt, is nothing but minus 1 over square root of 1 minus alpha t bar epsilon naught. So actually, you don't need to calculate the gradient because the gradient is nothing but your noise, but scaled by some factor 1 minus alpha t bar. So as it turns out, the two terms are off by a constant factor that scales with time, right? The score function. So what is the intuition of the score function is that how it tells you how to move in data space to maximize the log probability. Remember, the gradient is the direction of the steepest ascent, right? So this is basically a direction. So it is telling you that at xt, what is the direction that you should move in order to maximize the log of p of xt. And this equation is telling you to maximize the log of p of xt, you need to subtract this much noise from the data. So you see, this is like both of these things are intertwined. So the score or the direction in which you have to move in order to maximize your log likelihood is equal to is equivalent to denoising your corrupt data xt by some noise, by removing some noise or scaled version of that noise. So this is like quite cool, right? I mean, the score function is related to the denoising itself. So it's like intuitively, since the source noise is added to your natural image x naught to corrupt it, moving in its opposite direction, right? Because of this negative direction, negative sign, moving in its opposite direction denoises the image, right? Like you added epsilon to get the noisy version xt, so you need to go in some other like opposite direction in order to denoise it, right? And that denoising direction is equal to your score fun the is equal to the score direction, right? Or the direction in which you have to move in order to maximize your log likelihood. And this is the mathematical proof that justifies this intuition. So so this is what we have shown that, learning to model the score function is basically equivalent to modeling the negative of the source noise up to some scaling factor, of course. So these are the three equivalent objectives to optimize your diffusion model, like learning a neural network to predict. So what are the three equivalent versions? The first one is to predict the original image X naught that we saw earlier. Then the second version is to predict the source noise epsilon naught. And the third version is to predict the score function directly. So yeah, so this is, I think, all there is to diffusion model for that we are going to cover. There is much more than it. I mean, there are many other things that like diffusion models, in fact, is sort of a hot topic right now. I mean, people are working on it. There are many things if you want to learn. There are several things that you can see. There are many papers, theoretical as well as empirical. You can see, look at those. But yeah, this is, I think, enough for understanding the basics and a little bit of intermediate diffusion models. So any questions here? Otherwise, we'll stop today.
No, I mean, by and large, I have understood the idea, I mean, behind this here.
Okay. Okay, so let me stop the recording and I will tell you, I will post on the group when we'll take the next lecture. Yeah.
Sure. Thank you so much. Bye.
Yeah, sure. Thank you. Bye.